Okay. So, last time basically we talked about the initial things about the structure determinations. We already said that heterocycles require special kind of attentions with regard to the structure determinations, simply because they are proton poor, right. And in heterocyclic chemistry, carbon 13 also is a very useful tool. In addition, nitrogen 15, these are the NMR tools. But before we talked about NMR, we also briefly talked about the mass utility X-ray. X-ray is the ultimate answer, but certain cases we have cautioned you that it could be also misleading, like the example of kinamycin, if you recall. And then the ketoenol tautomerism, that is best studied by UV. Of course, it has to be supported by other things, other means NMR, other things. And then when you came to the one dimensional NMR, actually when you come to a one dimensional NMR, we normally deal with three different parameters, right. What are the three parameters? These chemical shifts, and then size and the shape. That is true also, that is actually also true for all all kinds of the nuclei, including whatever the 40 to 50 different nuclei, NMR active compound, NMR active nuclei. For all these nuclei, actually all the three parameters are equally important, fine. We gave you examples. Okay. When I say chemical shift means it is basically delta parameter, right. And when I say size means integration, and shape means multiplicity. Okay. And so we have seen that in case of benzene, whatever the chemical shift is in pyridine, just basically electronegativity is one of the important guidance. Okay. In case of pyrrole also, with reference to benzene, this pyrrole is considered to be pi excessive heterocycle. This is a term, pi excessive heterocycles, right, because a pair of electron is shared by 5 atoms. So, this is that is why it is pi excessive, the electronation increase. So, chemical shift decreases, that is the typical. So, that means from there you can make out whether you are dealing with a 5 membered or a 6 membered, which are more commonly encountered in the chemistry. And then also we looked at the coupling constant. We gave you a very important guideline. What was the guideline? That with increased electron density, with increased electronegativity, the coupling constant decreases. So, this is a very important guidelines. You can quickly distinguish whether you are dealing with a 5 membered or a 6 membered or with a heteroatomic compounds or not. Okay. And there are many other factors which influence the coupling constants. Then we also gave you some of the examples of these, right, NH carbene, NHC carbene. Okay. So, NHC carbene that we have checked that even a small molecule which was thought to be a sidnone or mesoionic compound, only in 2012 it was found to be a stable carbene, that is called nitrone, right. Today what do we do? Today we basically will have again little bit of the chemical shifts, little bit of the coupling constant we will ignore, but we will exclusively talk about nitrogen 15 NMR, and also we will talk about 2D NMR. 2D means application of 2D or in 2D NMR application. So, all of us know the 2D NMR. What is 2D NMR? How does it differ from 1D NMR? What is the specialty? Abhishek? Okay. What is the specialty of 2D NMR?
So, 2D NMR describes the interactions between the special, say for each NMR, interaction between or coupling between two different protons.
Right.
Okay. Which is not expected by normal observation or something like this.
No. Okay. So, basically yes, what you said essence is correct, but to be more precise, it only deals with coupling. How is that?
Yes.
Only deals with coupling. Okay. So, that means from the 2D NMR you get coupling information. So, in that just to very briefly introduce, okay. So, that means what do we do normally in NMR, what do we do? Delta, right, then integration means how many protons, etc., and then multiplicity. These are the three things often. This is in 1D NMR. In 2D NMR basically we deal with multiplicity. Multiplicity, this is basically is referred to this coupling, that is all. That means, the coupling information is embedded in a 2D NMR. Now, let us look at a 2D NMR of, for example, chloroform, for example, chloroform. So, what is the expected 2D NMR of chloroform? How many contour you will be finding here? Let us say, when I say chloroform means proton NMR. The proton NMR, whatever the in case of 1D NMR you get a single hydrogen, that is all. In the 2D NMR, what do you get? Nothing, again a single contour. That means, you do not get any additional information, that is important. That means, where there is no coupling, 2D is useless, as simple as that. So, in heterocyclic compounds, where as you know, most often protons are less. So, obviously couplings are less, but there are other things also. So, in 2D NMR, then what are the other items often we deal with? There are two. So, all kinds of spectroscopy in 2D ends with COGI, right? COGI NMR, or correlated spectroscopy, basically correlates the couplings, the nuclei which are coupled to each other. And then under this COGI, this is called homo-COGI, means the implies. So, hetero-COGI means hetero-atoms, and then that means sometimes called homo-COGI spectra and hetero-COGI spectra. Then what else you have? The other categories are HMQC. HMQC H stands for heteronuclear multiple quantum coherence. So, it is a basically 1J coupling. How is that? 1J coupling. 1J coupling means for example, let us say you have a coupling with between this carbon and hydrogen, and the number of intervening bond between them is 1. So, this is called 1J coupling. If these sort of couplings are shown in a spectrum, that is in a 2D NMR, that is called HMQC. Sometimes we call HETCOR, means heteroatom correlation spectroscopy. When I say heteroatom HETCOR, so what it means, actually there are plenty of other names. HETCOR means it is basically 1J coupling, 1J coupling. Then one more important kind of spectroscopy or 2D technique is this is one of the very useful one, HMBC. HMBC I do not have to write, this is again a heteronuclear, and M stands for multiple and B stands for bond and correlation. Normally this refers to 2J, means 1J is skipped, that is important. I mean direct coupling is avoided, then 3J and very rarely 4J. Actually, I have just once upon a time I came across this 4J. So, these are the techniques. Now, then you have all kinds of sub techniques. Sub technique means, like in this case, what when I say HETCOR means carbon hydrogen, it could be nitrogen hydrogen, it could be any other hydrogen. So, similarly, HMBC talking about, when I say HMBC talking about, is essentially it is in HETCOR, it is in HETCOR. So, heteronuclear name implies a heteroatom. Now, it could be 2J, 3J, they all are in the same spectra, though, by the way, they are not separate spectra, they are all in the same spectra, same spectrum, and then you have to be little cautious about this 4J. It could be seen, it could not be seen, but quite often 2J and 3J are seen. Not only that, the nuclei could also be differing, means let us say, like in this case hydrogen can undergo coupling with 13C, and hydrogen can undergo coupling with 15N, all kinds of things. So, that means it could be of different kinds, but most commonly that is hydrogen is one of the commonest nuclei, because it is populous, population is very high. So, these are the techniques normally we deal with, but basic idea is chemical shift, size and the coupling, nothing else. So, throughout then other special techniques all of us know NOE, right, nuclear Overhauser effect. Overhauser is the name of a scientist. Then now people say NOEG, this is 2-dimensional equivalent of this one. This basically gives you again a coupling, but direct coupling, not the indirect coupling. There are two terminology often used, direct and indirect. Direct means through space, there is no perpendicular distance, and indirect means through bonds. Okay, that often we deal with. Okay. So, that gives you the direct coupling, and then there are many other techniques actually we do not often use it. There is a called TOCSI, I think TOCSI, something like that, TOCSI, sorry, TOCSI, total correlation spectroscopy. So, it actually contains all the couplings, all the direct couplings, all the indirect couplings, but the spectrum becomes, all of you can understand, becomes too complex to understand. Okay. So, we have other thing, there is called ROAG, remote correlation spectroscopy. I never come across that, but people use it. Then some people use DOSI. DOSI is diffusion correlation spectroscopy, something like that. So, I think this is used by mostly the physical chemists. They use solution structure, solution dynamics, all these things are like Professor Nilmani Sarkar uses DOSI spectrum. Okay. Suppose you have an amine bound to a solid surfaces and freely floating in the solution, how do you differentiate them? Both of them would look alike in the NMR, but if you by using DOSI you can differentiate them. Okay. So, we have, but for us for practical purpose, what are the things? Will be 1D, that is good enough, which could be with respect to hydrogen, carbon, and HMBC and HSQC, that is all. Okay. So, we will just now with this little background, we will look at maybe some of the examples only. In certain cases we will exemplify the chemical shifts, certain cases the correlations, certain cases the trends. Okay. And in between we also talk about these exclusively actually nitrogen NMR. Maybe okay, we will begin with nitrogen first, that would be nicer. Let us say nitrogen NMR, what should we know? The active nucleus, by now all of us know, right. Active nucleus most often used in NMR heterocyclic chemistry is nitrogen 15. What is the I value? Nitrogen 15 I value? It's half, right, half. And what is the frequency? That also you have to know roughly. Let us say if hydrogen has frequency 100 megahertz, then what should be the frequency of carbon? 25. All of you know, good, 1/4. So, similarly with reference to hydrogen, what is the nitrogen frequency? Nitrogen frequency, it is much less, I think around roughly I can just guess it is less than 25, that is for sure, less than frequency in that region. Why do you need to know all these things? Simply because when you adjust the machine, you have to see where to fit it. I mean, of course, these days every channels are already fixed, nitrogen channel, hydrogen channel, carbon channel, they are fixed, but you have to know at least on which side you have to look for. Okay. Number one. Number two, that sometimes dual probe, multiple probe, you have to handle all these things if you grow up. Okay. Any case, so this is important, and the sensitivity, and then all of us know now, I think what I said, the natural abundance is 4%, 0.4%. This is very less compared to the most populated one is hydrogen, all of us know, followed by, I mean, fluorine. Fluorine frequency is close to hydrogen. Then comes phosphorus. Phosphorus I think is phosphorus also 100%. Then the carbon, most often used is carbon 1.1%. So, even the nitrogen 15 is less than that, that means less sensitive. So, you have to have more scans, but that is not the all, that is not all. If the frequency is not adjusted, it can overlap with nitrogen 14 frequency. Nitrogen 14 also very close to the nitrogen 15 frequency. So, you have to be little cautious about that. And then nitrogen 14 has a quadruple moment. So, that means I equal to 1. So, what it does, it actually induces faster relaxation. Induces faster relaxation means this I mean, if you just apply the uncertainty principle, the signal will flat with just merge with the baseline. So, that means you may not see it. So, you have to, that means that is the reason why it is not followed, but it has some advantages also. If you have a carbon, if you have a hydrogen attached to a nitrogen, you can almost always see some sort of broadening. Let us say you are expecting an OH and an H in the same region. How to distinguish them? There are, if you try to do the exchange experiment, it can be applied to the both. That will not distinguish NH and OH. Then how do you do? Just after exchange, you will see the broadening is retained with the case of nitrogen, not with the hydrogen. Sorry, not with OH group. So, that inherent broadening also there. So, that is helpful sometimes. Any case, but there is another disadvantage actually. The disadvantage with nitrogen 15 NMR, that nitrogen 15 relaxation time is pretty high. Relaxation time for what is the relaxation time of hydrogen, let us say. These are the things you have, these are all the common vocabulary taken from NMR course. Or what is the relaxation time? Rough idea. Relaxation time of hydrogen, relaxation time of carbon, roughly.
Carbon some 2 to 3 minutes.
Good, very good, very good. At least it can be up 5 minutes also, 5 months also. So, and for hydrogen, microsecond, 10 to the minus 6 seconds maybe, I mean less than 1 second for sure. Okay, that means that tells you how much relaxation delay you will be giving in the machine. Okay. For nitrogen 15, it is about 100 second. 80 second actually, 80 second. So occasionally what you do now, here you come with this inorganic people. Inorganic people would come, they will put a chromium complex with acetyl acetonite complex of the chromium 3. What is it? It is a paramagnetic substance. If you have a right paramagnetic substance, it optimally induces the relaxation. That means relaxation time decreases. If you have paramagnetic substance, relaxation is faster, signal is broadened. In this case, what you do? Yes, maybe signal is being broadened, but at the same time you are compromising with the relaxation time. Okay. So, that means occasionally depending on the situation, etc., you will do this. And next most important thing in nitrogen NMR is reference. It is a critical reference. Actually, this morning also I got confused. In one node I had something like minus 8.5, the other node I got some 300, 400 for the same compound. I really got confused. Then I had this visitor also, I asked him, he is from Oxford, today's seminar speaker. I asked him, have you ever used NMR nitrogen 15? He said no. Okay, but he could not say which one is the reference. So, recommended reference is nitromethane nitrogen. This is the reference, internal reference. Okay, but this is recommended by IUPAC. But unfortunately, people do not follow. People follow external reference. This is a liquid ammonia. So, this is actually external reference. Okay. So, whenever you look at a nitrogen NMR, you have to be little careful about it. What is the reference? Okay. To give you a hint, if you are, let us say, dealing with nitromethane, so whatever the chemical shift you get, that's if you want to convert this into liquid ammonia. So, what you do, you just take this nitromethane chemical shift and plus nitromethane chemical shift plus 380 ppm. So, if you follow that, then that goes to the reference of liquid ammonia, and normally the range is from 0 to 500 ppm. It depends. Why?
Why they don't use that? Naturally, IPC recommended.
That is up to the convenience actually, it is convenient up to the convenience maybe, because you see externally means once you standardize, then you can routinely do it one after other, you do not have to add nitromethane, that is all. That is the reason probably, but some people have used liquid nitromethane also. I have references, and for example, Silverstein reported again with liquid ammonia, and but then I consulted a review article that also used liquid ammonia. So, all these things are mostly, but there are examples where so that is important, right. And at this chemical shift is very important in this case. Chemical shift range is high, but unpredictable, quite unpredictable. So, whenever you are required, you just go consult a book and see the trend. For example, I will begin with the smallest heterocycle aziridine, and in this case this delta nitrogen here is minus 8.5. When I say so, basically it is referred to liquid ammonia. Okay. So, that is the oldest reference. So, that is followed. Now, begin with now just put one more methyl. So, I mean anybody can predict anything actually. I mean with my understanding I would predict a higher chemical shift value, and it has been true in this. And the explanation many of you know, it is not electronegativity, not really. If the electric density increases, chemical shift decreases, but in this case chemical shift increases.
Carbon is more electronegative.
Carbon is no. Okay. So, I will take you back to the, I do not know whether I taught you NMR, I do not in your class, no, okay. This is very important. For example, just quickly then go through quickly. Let us say we are talking about the ethanol, let us say, okay. These two examples, let us say. So, this is a hydrogen up here, and this CH2 ethanol and isopropanol. Okay, underline hydrogen. What should be, which one will have a higher chemical shift value? Ethanol or isopropanol? Isopropanol should have a higher chemical shift value. Why? Of right. That's it. It is not the inductive effect. Often we get confused with inductive effect. It is the carbon-carbon sigma bond that gives you this. So, this is the reason why in this case of aziridine you can say so. Okay. And then but these are all, there are plenty of examples. For example, if you just take an example of let us say aziridine, the substitution elsewhere at the 2 position, then the delta nitrogen would be coming to again is delta nitrogen is as a 10.5. So, delta is increasing, delta is increased again. Okay. So, I mean all these are all the standard value of the let us say for example, in case of just typical value here, typical value of pyridine, it is 314. So, you can just make out from these things here, and let us say that means you can quickly distinguish aromatic and aliphatic. For example, this is a known compound, right? Quinine is a known compound. All of us can quickly write this structure quinine. How do you write this? 314, right? Quinine will have so OH up here, and then you have a aza bicyclic system, right? Aza bicyclic system. I mean, I am just giving you a rough idea. Do not worry about this thing here. There is a nitrogen up here. So, there are 2 different nitrogen. In this case, it is this aromatic nitrogen is 295 and aliphatic nitrogen is 28. So, it is clear. That means, this spectrum, how would this spectrum look like? How would this spectrum look like? Just basically, if you let us say begin with 0 here, 28 here, let us say you make it 300. So, that means that's all. That means, you will have only 2 lines. So simple, very simple. That means, if you have access to nitrogen NMR, you can quickly look at these 2 stuff without any problem. Okay. And so,
Sir, what is the moiety corresponding to 28?
not moiety, it is the nucleus, nitrogen.
No, sir, I know, but I want to know that means a ring. What's the ring?
Oh, ring is
Actually, I can't see that. That's why.
right, but those guys said okay. Any case, he say as a bicyclo 2222 octane. How is that?
As a
Bicyclo 222 octane. Okay. So, okay. So that means we have given you enough background. Now let us have examples only, the techniques and this. So enough. That means aromatic nitrogen will have higher chemical shift, aliphatic. That's quite obvious. So, but whenever you are dealing with a right problem, you have to just go through the literature and find out what are the set of the values. You know, don't try to remember all these values, but you have to know how to use the techniques. Okay. How to use the technique means you have to know what to know about the techniques and what to know about the structures, etc. All these things. Just we will have from now onward, we will have only a few examples. For example, I have a problem here. Imidazole problem. Let us say imidazole problem. I think by now all of us know imidazole means it is a 5-membered ring with 2 nitrogen, and that you have to remember because it is a biomolecule. So, you have to remember like this. Now, this is an example because it is a very commonly encountered molecule. Right. Okay. Actually, the imidazole itself is not really soluble in organic solvents. So, what you do? Actually, you put a little bit of sulfuric acid. Occasionally, what do you do? Trifluoroacetic acid. Trifluoroacetic acid. Many times you have done it. Many insoluble compounds, they are insoluble. So, you just add you are expecting a basic nitrogen, put trifluoroacetic acid. So, and then it gives you this salt here. Now, so what is the difference do you expect? So, obviously, the chemical shift should be increased because you have added a proton, positive charge, and that is what you see. This is 8.6. So, like this, all these, I will not give you the value here, but what is important in this case, that I like your attention to be drawn to the fact that very interestingly, let us say this hydrogen and this hydrogen, that means is coupled in the NMR. That means, number of intervening bond between this the indicated hydrogen, this one and this one, 1, 2, 3, 4. Normally, 4 bond coupling are very very little. In this case, it is significant, and the value is here 1.4. Occasionally, it can go up to 2, 3. Okay. So, what is the reason? Reason is all the carbons which are sp2 carbon atoms. sp2, if the things are in the system, you have plenty of sp2 carbon atoms, then you can go up to 9 j. That means 9 bond intervening number of intervening bond could be up to a maximum 9. I have seen up to 11. Okay. So, provided those are only alene systems. So, this is just an example, that means where you can find out the coupling can be existing even if you have a 2,5 hydrogen. Okay. And then there are other thing, I think. Okay, this is a case, I think we will ignore that. I will come back maybe sometimes later. Okay. Let us say okay, we will have an example of HMBC, HMBC, okay, and HMBC may be taken from it's a case of let us say if you have a structure of this kind, it is a coumarin, right, and nitrogen and this, okay, and this structure also is isomeric to the structure what I am writing on your right, rather on my right, it is something like just exchange the nitrogen and oxygen up here, just interchange the position of nitrogen and oxygen. So, how do you differentiate them? Isomeric. So, the mass spectrum will give the same mass, same molecular formula is same exactly, it is very difficult, it is very difficult. But since we know now that HMBC experiment, so one can quickly decide. Let us see. So, what is the starting point of HMBC? Starting point of HMBC, what could be the starting point? Where do you start from? In NMR analysis, any NMR analysis, you have to have a nice reference. For example, Sam yesterday made an acetate, right. So, whether the NMR is correct or incorrect, how do I know? We start from acetate, because we know acetate comes almost always at 2 point something. So, if that is there, the compound has to be there. With reference to that, we just explain. So, similarly, here also you have to find a proton or something which is for sure existent or and giving a signal. In this case, which one? Methyl. Methyl is a nice singlet you can just see. So, but it does not undergo any coupling, right. You have a CH3 here, okay. HMBC means, let us say for now we talk about carbon 13 for example. What do you see? Okay, I will make it 2 here, I will make it 2 here and hydrogen, fine. HMBC takes care of 2J, 3J most commonly. So, that means this hydrogen would undergo coupling with 1, 2, that means this carbon, this one, this carbon, okay. So, that means this would undergo coupling. So, similarly, this hydrogen would undergo this carbon would undergo coupling with this. So, in both the compounds you have that coupling. So, you cannot really make out, right. So, what do you see actually, how does the spectrum look like? Spectrum look like, let us say if this is a proton scale, this is a carbon scale. If you have a spot like this, that means just basically a vertical line and horizontal line, okay. That means this hydrogen is coupled to this hydrogen, that is all. Unlike in 2D co-G NMR, you look for cross peaks, okay. So, just basically just a sort of a linear connectivity kind of things. So, that means if this is the hydrogen up here and this carbon, let us say is this, just supposing. So, that means in both the cases you will have a very similar chemical shift, similar coupling. So, you cannot distinguish them. So, what else you do? Go to the 3J. 3J means 1, 2, 3. That means this one would be coupled with this original hydrogen. This one would be coupled original hydrogen. You can see the environment; they are very much alike. So, it is very difficult to distinguish. That means there would be a spot corresponding to that one. That means this hydrogen, let us say, would also have a spot here, and this one is the second carbon. Let us say second carbon. So, that means this hydrogen would also couple to another carbon, but it does not differentiate them, right. So, what do you do? Okay, let us take another reference. What is the reference? Here is a hydrogen, right. This hydrogen is distinctly different from all other hydrogen, reason being close to aromatic, close to second aromatic. This one is an aromatic one. So, influence of aromatic would make this one distillate. just like naphthalene perihydrogen. Naphthalene perihydrogen is more desilted than the other peripheral hydrogen. Okay. So, that means it will be most downfilled hydrogen in aromatic region. So, let us look at the HMBC of that one. So, HMBC means okay, this is our reference 1 and 2 bond, that means this should be coupled, this one would be coupled. So, in this case also you have a coupled hydrogen. Then 3 1 2 3, this one will be coupled, in this case 1 2 3, this one also would be coupled. Mind it, here you have oxygen, you have nitrogen, it is very difficult to distinguish the chemical shift wise, because both are electronegative, both are aromatic systems. So, it is kind of difficult. So, you have to have something which would be unambiguous. So, what should I do? What should we do? Okay, let us see. We will do again HMBC, but in this case we will do HMBC with nitrogen 15. How is that? Nitrogen 15 means what you see, let us say again, in this case on the leftmost hydrogen is this one and the bond is 1 2, that means it can couple this hydrogen, in this case also this, right, and then 1 2 3 it can couple with this, in this case also 1 2 1 2 3. So, it does not make any difference, but if you come with the other reference hydrogen, methyl hydrogen 1 2 3, that means hydrogen couples with nitrogen, in this case hydrogen coupled with nothing, oxygen does not couple, that is what it is. So, quickly, that means that these are the things you have to just look for. In fact, we never did any nitrogen HMBC, but in this particular example nitrogen HMBC is perfectly all right. Okay. And this is very useful, especially in case of nucleoside chemistry. Let me see if I have an example. Example maybe let us say nitrogen HMBC. So, I have okay. Let us look. I do not have an example of nitrogen HMBC. So, all I have is a carbon HMBC. Okay, let us try with one carbon HMBC and see whether we can distinguish two isomeric compounds which are heterocyclic. Again it is a quinolone derivative, quinone kind of derivative, heterocyclic quinone, and you have this thing, then you have a hydrogen up here and it is an aziridine kind of structure. Similarly, one can guess this versus you have again a quinone, it is a pyridine nucleus, just interchange the position of aziridine and the hydrogen. Okay. So, now the problem is to what technique would you use to differentiate them? What technique would you use? How do I know what technique? Where to start with? Let us say, just give your answer first. How to start with? Structure given. Oh, okay. Structure given. Now, just tell me where to start from. A reference point. What is the reference hydrogen? This hydrogen. Because it is para to nitrogen, because of the all of us know, because of the resonance effect, this hydrogen is most desilted, number 1, and then you have carbonyl anisotropic effect. This oxygen is facing the hydrogen. So, you have a strong anisotropic effect on hydrogen. So, this hydrogen would be most desilted. So, that means you start from, that means very quickly actually whenever you come across a heterocyclic the spectrum, where do you look at actually, left, right, or most populated or less populated area? Less populated area, that is right. either you extreme right or left or less populated area. So, exactly so you do the same thing. This is important, the starting is very important, starting and your confidence in assigning the reference, that is important. Okay. Once you have a right confident reference, then the rest of the problems should be easier. Okay. So, that way, so you have these two then, and then let us see, I mean whether you apply homocogy, heterocogy, all these things. So, you know all the meaning, but since I have already told you that we will be dealing with each HMBC, let us see what happens. I mean if you just deal with, let us say this one 1 2, that means the carbon here, second carbon, then 1 2 3 carbonyl carbon, right. So, angular carbon and carbonyl carbon with this, right. So, similarly here also you see angular carbon and carbonyl carbon. Okay. Let us say then what else, you can see this most upfilled hydrogen, this is not an aromatic hydrogen. So, it should be most upfilled hydrogen. So, what you see here, this one again a carbonyl carbon and what else 1 2 I mean you can say nitrogen carbon. So, 1 and 2 nitrogen and 1 and 2 nitrogen. So, you cannot really differentiate, right. So, what to do? So, what to do?
So, if we move to proton coupled carbon 30, proton coupled carbon.
Normally people these days people do not use. When we did PhD we did that because coupling constant is so high, I mean the whole spectrum becomes too complex. I do not know whether you have any idea about the coupling constant. Direct the coupling constant of carbon and hydrogen could be 120, 200, 300, 400, 500. So, you can have hodgepodge in the spectrum. So, the quickest I mean although this there are ways to solve this problem. If you have just basically these come from confidence level. For example, all of us know the chemistry part, right. Chemistry part means if you look at this nitrogen lone pair, it is some conjugation, although it is not fully conjugated to this carbonyl group. Okay. This carbonyl group, that means some conjugation is there, the chemical shift would be decreased in this case. Okay. So, that way you can find out which one is para conjugated to the nitrogen. In this case, the one this here is para conjugated. So, that way one can determine this answer. I think the one I have here, has no definite answer, but they did this experiment. So, best thing probably would be which one? Nitrogen? No, nitrogen also would not do anything, because you have hydrogen here 1 2 3, in this case 1 2 3. So, nitrogen also would not help. So, only thing the way one can do that distinguishing these two carbonyl first. Once you distinguish these two carbonyl first, then we can go for the analysis. So, essence is what is the essence? The things are not that easy, in certain cases quite easy, depending on the situation, whether you switch to carbon, we switch to nitrogen, but you have to have all this thing in mind. Okay. And let us I think by now many of you know, for example, in this case there is an experiment also all of you know this NOE experiment. NOE experiments, what does it demand? It demands that the two nuclei should be close enough. When I say close enough means this is an absurd answer. You have to have a how much?
0.2 to 0.4.
No, much more. It's close to 5 angstrom. No, close to 5 angstrom. Twice the hydrogen bond. What is the max? What is the hydrogen bond? Standard hydrogen bond distance? 2.45 or something like that. So, roughly that. So, just below 4, below 5. Okay, it's just a random guess, but point something is not for sure. Okay, maybe I am wrong. Okay, if I am wrong, you just no, it's possible. It's possible. Okay, but any case, that's what you have to. Whenever you just try to do NOE, you have to make sure that these things. Okay, and so I think if you know NOE, then I will give you a give you an advanced problem actually, advanced problem. For example, okay, let us say how to distinguish. This is again an experiment to distinguish isomeric compound. Okay, and in this case, the structures are again say bicyclic structure, nitrogen. This is NH2 and OH, and this is OMe, and the other compound that we like to look at would be again a isocovalent derivative. This is OH and NH2 and OMe and OMe, right. So, how do you distinguish? Tetrahydroisocovalent.
Alpha hydrogen to nitrogen.
Tetrahydroisocovalent. So, how do you do? That means this portion is common. So, only thing that one CH2 group is just exchanged. This whole CH2 group has been placed here. So, rest of the things are all right. How do you do? Number of benzenic proton here. 2 here also 2. Here also on this side. Benzylic marginally different. Will have little difference. Yes, integration will. Chemical shift. It's difficult. It's difficult. If you let us say if you often we deal with tetraline kind of compounds, some with it's difficult to deal with. Okay, how is that? Okay, I will accept your answer, but you have to support it by another complementary technique. Just suggest a complementary technique. Okay, let us. I mean, or I can straight away ask you this question. Just do a kind of derivation so that your NOE study would be better off, means would be more suitable. That means one of the requirement of what I said, the nuclei should be in close proximity, that is one of the requirements. The other possible requirement, that means to make this to bring the nuclei in close proximity, what you have to do? You have to cyclize. So, that means if you have some kind of derivative you have to do, it just basically you have derivatized, so that these hydrogens and things or something comes in close proximity. Okay, in this case actually what is done, I will just give you the answer. This answer is here. It is a phosphorus oxychloride, oxydichloride, triethylamine. I just give you only one example, probably the top one, and this example would be. So, I will just quickly write, and oxygen, just one can quickly also write the structure, right. This phosphorus here and NH, that is a cyclic structure, that is all. What else? What do you see? So, what you will find, if you just think of the structure in 3 dimension, this is let us say pointing towards down, and you have hydrogen up here and you have a hydrogen alpha hydrogen. You can visualize that this hydrogen will have an NOE effect, but if you write the corresponding structure here, the alpha, the hydrogen of the CH2 on the other case, in this case that this one is far away from, that is all. So, that means by cyclizing the compound you have brought one of the groups to a neighboring hydrogen, that is all. So, you can do this, that means this is just a trick. So, many times if you have, let us say you are suspecting, let us say diol compound, many often will make diol. What do you do? Find out the stereochemistry of the diols tough, because they can move, they can rotate, all kinds of possibilities. So, you just convert into corresponding acetonite and the acetonite, that is one of the trick. Other trick is the corresponding sulphate I guess, sulphate or sulphite, something like that. So, just thionyl chloride, so it should be sulphite. So, convert it into sulphite and you get the corresponding things. Okay. And so, I think we have many more examples. The last example, this is a nothing to do with the 2D NMR. It is an example of the multinuclear NMR. Let us say, this is let us say who will take up this. Okay, Susmit, this is your homework. Write a term paper on BODP dye. BODP, Bo stands for boron, dye stands for dye, and this is pyrrole methene, a group of dye. It is a fluorescent dye, very important fluorescent dye these days. Okay. Someone recently, very recently in 2011, JOC, I will give you the basic reference, so that you do not have to spend much time. Okay. This is the reference. What they did, they took a compound, dipyrrole methane compound, okay, and so this is dipyrrole methane compound, fine. And they have done a series of reactions. I will just you work out mechanism by yourself, or you can look at the literature. DDQ, all of us know DDQ, dichlorodicyanoquinone, is an oxidizing agent. Then he put extra pyrrole. Eventually, what he got a compound very similar to this, this one 5 membered, again on this side 5 membered. So, and then he got also an additional 5 membered pyrrole. Okay. And so, something this, then this, then in between, actually what he did BF3 and triethylamine. So, it is a 3 steps reaction. So, what is the suggested product? Suggested product is say boron, and this is coordinated, and this is this. That means, now it is a BF2. So, BF2 has been incorporated, one fluoride is expelled. Now, how do you confirm it? We do not go to wet lab and do that, we will all go to the spectroscopy lab only. How do you know there is a BF2? BF2, how do you know? Spectroscopically. NMR? So, which NMR? Fluorine, fine. Okay, so 19 fluorine. So, what should be the nature of the peak? What should be the so you will get a singlet, right? No, what is the multiplicity? Huh? See, mind it, how to evaluate coupling, rather, or when I say that coupling would take place, which sort of coupling would you see? For example, quickly, okay, I will give you the okay. Let us say you have something like this, right? What do you see about this? You will say a doublet because of this hydrogen. We always just jump to 1, 2, 3, but you are ignoring the fact that these carbons also have a nucleus called 13C. That can also coupling, that can also coupling, right. So, you have to take care of the abundance. Abundance also you have to keep this in mind. So, whenever you study the nuclei, you have to have the frequency known, you have to have the spin quantum number known, you have the abundance known, and then whether it will appear or not appear, or whether you will see or not see, that all depends on your spectrum. Okay. Many times we call satellite spectrum, satellite peaks. The satellite peaks are nothing but those small couplings, small invisible couplings. Okay. Any case, so in this case, what you will see that boron. So, that means boron would split this fluorine. What is this splitting pattern should be? The formula is 2 Ni plus I. In this case, N is 1, boron 11 is 3 by 2 and quartet. So, it should be quartet, fine. What else? Nitrogen population is very low. So, but this hydrogen. So, 1, 2, 3, 4. 1, 2, 3, 4. So, 4 bond coupling. 4 bond coupling is possible, and because you have an sp2 atom here, boron is electron deficient. So, you have sp2 crowding. So, it should be, that means this is fluorine would appear as a doublet of a quartet. Okay. So, likewise, so what should be the splitting pattern of the boron then? Boron. So, you have to think about this. Fluorine is highly population is very high. So, that is why you could see the hydrogen coupling also, but in case of boron the population is not that high, but so boron should be split by only fluorine. So, what should be the multiplicity? Triplet. So, like this actually you can just quickly establish that boron is there, fluorine is there without much problem. It has been a regular practice now. I mean, so routinely heterocyclic chemists do all these experiments. Okay. So, I think we have talked about most of the important things. I think, I guess then it is a matter of practice and use. I think we will take care of. Okay. So, next time, next class we will be talking about actually the reactivity. What does nitrogen do? List, let us say the question, I leave you the question. Let us say you have a carbocycle, you put a nitrogen. What sort of reactivity difference do you like to see, which will arise out of nitrogen? Cyclohexane as a cyclohexane, for example,